Hi everyone, we're moving on to chapter 12. Today we're going to work on 12.1 operations with radicals. In chapter 12 you're going to be working a little bit with square roots. You're going to see a little bit of the Pythagorean's theorem, which some of you might have seen that already. You're also going to be working a little bit with the distance and midpoint formulas. So let's get started in 12.1 working with operations using radicals, so the square root sign in chapter 12.1. So there's a little property here, the definition of square roots, and I want you to become familiar with this property. When you have similar variables or numbers underneath the radical sign, remember the radical sign is the square root sign. This is it. Here we have the square root of a times the square root of a, which is going to give me a. Our second example here with this property is we have a negative sign outside the square root sign here. Negative square root of a times negative square root of a is going to give me positive a. So I want you to become familiar with these properties. Make sure you write them in your notes. Another thing is working with simplified radicals is sometimes you'll see x is equal to a positive square root of a, or x is equal to a negative square root of a, or number or variable. And sometimes we abbreviate this as x equals the plus or minus of a. And this should look familiar in a few sections ago when we're working with plus minus values when we're getting our answers working with square root. Let's go on and try a few examples working with simplifying radicals. And so let's look at a right here. We have 4 times the square root of 6 minus the square root of 6. The first thing we need to do, looking at this problem, is see if we have like terms. And if we do have like terms, we need to combine those like terms. Notice my like terms are square root of 6 and square root of 6. And then I have values outside of my square roots. Here I have 4 minus, we can put in a 1 right here to help us with solving this. So when we combine like terms, we can subtract 4 minus the 1 to get 3. And then combine the 2 square root of 6. Think of it like this. The square root of 6 times the square root of 6 is going to give me 36. And to take the square root of 36, you just get 6. So we're just going to leave it as the square root of 6 here. And this is going to be my final answer simplified for A. Let's move on to problem B. And again, we're going to look at like terms and simplify this. Like terms are my square root of b, square root of b. My other like terms are the values outside in front of the square root of b. So we have a plus 2 and minus 2a minus 3. Let's combine these two first. So a plus 2 minus 2a minus 3. Combining like terms, we have our a and a minus 2a, which gives me negative 1a, or we could just call that negative a. Combining a positive 2 and a negative 3 is going to give me minus 1. And then we have our square root of b, square root of b, so times the square root of b. My final simplified answer here is a minus 1 times the square root of b. And that is it. Another property in 12.1 that you might see is the multiplication property of square roots. And for this, it says all real numbers, a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of a times b equals square root of a times the square root of b. So we just separated out the variables and put them under their own radical sign. Let's look at before we do some examples, there's something called the simplest radical form that you'll be working with a little bit in this chapter. And what this is radical expressions are simplified to manipulate things algebraically, and it's easier. The square root expression is in simplest form when the following conditions are met. The first is no factor of the radicand is a perfect square other than 1. Radicand is almost, think of it as the square root sign. The radicand contains no fractions. So whatever is in the square root sign here, it contains no fractions. So maybe, for instance, we could take 35. That's what they're saying. And no radicand appears in the denominator of a fraction. All right, so let's do a few examples here now. Our first example is we're going to simplify the square root of 72 times m squared times n to the 5th. When you're solving these types of problems, you first have to look for perfect square factors. And when you look and find perfect square factors, we're going to pull them out and put them in front of the radical sign. Non-perfect square factors stay inside of the perfect square, inside of the radical sign. Do you see anything in here that's perfect square? Well, m squared is, because if I were to take m squared and take the square root of that, I would just be left with m. So I'm going to take this m and I'm going to pull it out and put it in front of the radical sign. So here we have m. Inside the radical sign, we still have 72 times n to the 5th. All right, so what we're going to do now is we are going to break apart the 72 n to the 5th. And I'm going to think of two factors that make 72. There are a lot of factors that make 72, but the two factors I come up with, one's going to be a perfect square number, for instance 9, times 8 gives me 72. 9 is a perfect square value, 8 is not. But we can keep breaking 8 down. What gives us 8? Well, 4 times 2 gives me 8. 4 is a perfect square number. 9 is a perfect square number. 2 is not. What is the square root of 9? That's 3. So I'm going to pull out a 3 and put that in front of the radical sign. So now we have 3 times m. What is the perfect square of 4? That is 2. I'm also going to bring out a 2 in front. So 2 times 3m. And that's what I've simplified out so far based on perfect square values. So now what I'm left with is outside of the radical sign, 2 times 3m times the radical of 2n to the 5th. Well, remember, n to the 5th is n times n times n times n times n. And n to the 4th would be a perfect square value. N to the 4th, we can pull that out. And the square root of n to the 4th is going to give me n squared. So I can put that in front here, n squared out in front. So then I'm just left with my n that's left alone. So after pulling things out in front of the radical sign, leaving left that 2n inside, my final answer is going to be n squared times 2 times 3 times m times the square root of 2n, because that's what was left over after we factored out perfect square values from the original problem. So this will be my answer for A. Let me erase this and then we'll move on to B. All right, looking at B, we have 2 times the square root of 7 squared. So what that means is 2 times the square root of 7 times 2 times the square root of 7. When we go to solve this problem, again, we're going to look at this and combine like terms and maybe factor things out after we've combined like terms. We're multiplying here. So what are my like terms? Square root of 7 and square root of 7. Square root of 7 times the square root of 7 is going to give me the square root of 49. So that's what I'm going to have after I multiply those, square root of 49. And 2 times 2 is going to give me 4, so I'm going to put that in front of the radical sign. Is 49 a perfect square number? Yes, it is. So we take the square root of 49, which gives me 7. So now what I do is I take 4 times 7, and I get a value of 28. And when we simplify the original problem, our final answer ends up being 28. And that's it for B. For C, for examples 2, we have the square root of 2 times 4 minus the square root of 8. Well, let's look at this, ladies and gentlemen. We have the square root of 2 and we have the square root of 8. And when I go about solving this problem, think of it like this. I am going to think of the distributive property. I'm going to take the square root of 2 and multiply it by 4. So what I have is 4 times the square root of 2. Then I'm going to bring down my minus sign here. The square root of 2 distributed to the square root of 8 gives me the square root of 16. Now, after I've distributed the square root of 2 to each situation inside the parentheses here, notice I get a square root of 16. That is a perfect square value. So what I'm going to do is I'm first going to take the square root of 16, which gives me 4. I'll bring everything else down, so I have 4 times the square root of 2 minus 4. Now, is the square root of 2 a perfect number? No, it's not. So what I'm going to do here is I'm just going to leave my final answer to be 4 times the square root of 2. Minus 4. Don't forget to put that minus 4 there. That's my final answer. The last property you're going to see in this chapter is, or this section 12.1, is division property of square roots. And what that means is for all numbers, for A is greater than or equal to 0 and B is greater than 0, the square root of A over B equals the square root of A divided by the square root of B. What you see that in the book and how it's going to look handwritten is A over B like this. It didn't come out on the computer very well. So when we break it down, it's the square root of A over the square root of B. Let's look at the first one. We're going to simplify the square root of 4 over 25. So what it really looks like is this, square root of 4 over 25. So think of it like this. The square root of 4 over the square root of 25. Is 4 a perfect square number? Yes. Square root of 4 is 2. 25 is also a perfect square number. Square root of 25 is going to give me 5. So my final answer for A is 2/5. Let's look at B. Let me erase this. B says we have the square root of 4 over 3. So think of it like this. The square root of 4 over the square root of 3. Now 4 is a perfect square number, which is going to give me 2. But notice we still have the square root of 3 here on the denominator. You cannot